In this video, we want to talk about the book Fooled by Randomness by Nassim Nicholas Taleb. In Chapter 7, Taleb introduces the problem of induction. We want to start with the following quote: "No amount of observations of white swans can allow the inference that all swans are white, but the observation of a single black swan is sufficient to refute that conclusion." In other words, the statement "all swans are white" is hard to prove, because the only way of proving such a statement with empirical data is seeing every single swan in the world and noting that all of them are white. Whereas refuting the statement can be done by observing a single black swan, or to be even more precise, by observing a swan which is not white. Taleb gives another example for the problem of induction in finance. Many people in finance tend to use past data to derive conclusions about the future, which can be dangerous. Generally, there is nothing wrong with analyzing past data in order to understand certain relationships in the market, but one needs to be careful with generalizations, because the fact that something never occurred in the past does not prove that this event cannot happen someday in the future. In particular, Taleb gives the following example: the market never goes down 20% in a given 3-month period. Now, it could be that the market never went down 20% in a given 3-month period, but that does not mean that the market will never go down by 20% in a given 3-month period. Let's discuss two problems with such a statement. One reason could be that the market changes over time and that events which never occurred in the past may occur in the future. Another reason is that the sample size is not big enough, in the sense that such an event occurs very rarely and that it therefore did not occur in the past, say, 20 years. But then it will happen one day in the future, even if the settings for the market did not change. In this simulation, probabilities do not change over time, so the problem can't be a changing market. Therefore, we want to focus on the second problem, namely a small sample size. For that, we model the market stochastically. We simulate the market development over time and analyze the underlying statement of whether the market goes down by 20% in a given 3-month period. We perform the analysis in R and use the following equation to simulate the market. Denote S of t the value of the market at time t. The market value at time t plus delta t is then given by the market value at time t times e to the mu minus sigma squared over 2 times delta t plus sigma epsilon times the square root of delta t. The parameters are chosen as follows: mu equals 0.1 and sigma is 0.15. Delta t equals 1 over 365. The intuition is that mu and sigma are given on a yearly basis and we want to consider daily development. By this equation, the market value at time t plus delta t only depends on the market value at time t and not on how the market got there. Note that the daily change, which is just S of t plus 1 over S of t, follows a log normal distribution. This plot shows one possible realization of the market. Now let's say we observe the market for 1 year first, which corresponds to the part of the plot where t is in the range from 0 to 365. To check whether the market went down by 20% in a given 3-month period, we take the value of the market at time t plus 90 and divide it by the value of the market at time t. We can conclude that for this particular market development, the market value did not go down by 20% or more in the first year. However, if we now consider the whole time span, which is 10,000 days, or in other words around 27 years, we actually find a 3-month period in which the market went down by more than 20%. For this example, it would be from day 6,695 to day 6,785, which can actually be seen in the plot. Of course, this is a very simplified version of the market and the true market is way more complex, but the point should be clear. We observe data for some time, let's say for 1 year, make a statement based on that, and then generalize it for all future events, which can easily go wrong. To apply the Monte Carlo technique, we now simulate a lot of possible market developments and not just one particular. We then check whether the market went down by 20% or more in the first year and whether the market went down by 20% or more in the whole time period. Running the simulation 5,000 times gives the following table. The market went down by 20% or more in the first year for 64 simulated worlds. In other words, in 4,936 simulated worlds, so in around 99%, the market did not go down by 20% in the first year, and some people might use this information to conclude that the market never does this. However, in 1,964 simulated worlds, so in around 40%, the market went down by 20% someday. Again, this is just a simulated market, and we could also change the time periods. Say, for example, observing the market for 10 years first instead of just 1 year, but the idea stays the same. It shows that past data does not always provide meaningful statements about future events.